Hello, we are going to note down some certain properties of binary trees. First, let's try to show a connection between height and number of nodes in a complete binary tree. And already we saw this fact, but let's just recollect it. What was the answer? So let's just try it out. A few complete binary trees, and so this is just one node, and height is 0, and number of nodes is 1. Okay, and this is another complete binary tree. Height is 1 and n is 3. So here height is 2, n is 3 plus 4, 7. Right? Okay, so let's write n and height. Okay, so what is the connection? What is the relation between height and number of nodes in a complete binary tree? So these are complete binary trees. What is the relation? So can you see that? It is n is equal to 2 raised to so let's just look at this. So this has to be, if I write 2 raised to h, what is this? 2 plus 1. So let's try this. Let's see whether this works fine. So 2 raised to 4. Yeah, this is not good. 2 raised to 2, 4 plus 1, 7 is not correct. Okay. So let's try this. What about this? 2 raised to h plus 1 minus 1. Let's do this here. 1, 2 raised to 4 minus 1, 3, correct. Height is 0, 2 raised to 1, 2 minus 1, 1 is correct. 2 raised to 2, 3, 8 minus 1, 7. This is correct. So this is true for a complete binary tree, right? Okay. So in a complete binary tree, the number of nodes is equal to 2 raised to height plus 1 minus 1. Now what about a general tree? Can you tell some relation between the height and number of nodes in a general binary tree? And we know that, right? So this n has to be less than or equal to 2 raised to h plus 1 minus 1, right? So I can write in a general tree, in a binary tree, I have this fact: n is less than or equal to 2 raised to h plus 1 minus 1. Why is this fact true? Because we know that in a complete binary tree you have all the nodes of maximum possible tree. A complete binary tree is a maximum possible tree. So any other tree of height h basically does not have a few vertices, right? If it's a non-complete tree, a complete binary tree of height h, it has some vertices missing from a complete binary tree. So therefore, the number of nodes has to be less than that. Right? So 2 raised to h plus 1 minus 1 is the maximum possible. And I can therefore write in any binary tree, so this is in any binary tree, n is less than or equal to 2 raised to h plus 1 minus 1. Right. What about this? Can I write something here? Connection with the height. Let's see that. Let's draw a tree like this. A tree which is basically just a height tree. So okay, so this has height 1, 2, 3, and number of nodes is 4, right? So n is okay. So this is the minimum tree of particular height. A minimum tree of particular height is basically just one line of, it's called as a path. So it's just a path of that many vertices, right? And therefore this is the minimum possible tree of a particular height, and this is the maximum possible tree. So complete binary tree is a maximum possible tree of a binary tree, and a path is the minimum possible binary tree. So this is a path, it's a minimum possible binary tree. And so we have now the following equation. In any binary tree, this equation holds. Okay, good. Now let's go to the next question. Can I say some relation between the internal nodes of a tree and its, let's say the number of nodes and internal nodes of a tree? Okay. Okay. Now, so let's look at the complete binary tree. So how many internal nodes? 0. Number of nodes is 1. And how many internal nodes here? 1. And number of nodes is 3. Here number of internal nodes is 3 and number of nodes is 7. Can we try to see the number of internal nodes in a complete binary tree? Do you have any idea? Okay. So it's something like 2 raised to 2 times, sorry, not 2 raised to 2 times. So let me just write and let's see this thing. 2 raised to number of internal nodes plus 1. The number of nodes in a complete binary tree is equal to 2 times number of internal nodes plus 1. So this is for a complete binary tree. Okay. So for any complete binary tree, the number of nodes is equal to 2 times number of internal nodes plus 1. Now, can you prove this fact? Why is this true? This is true as we can see, this is true in the example. But why should this be true in general, right? How will you prove this fact? This you prove by induction on the height of the tree. And what is the base case? So I'll just briefly tell. I'm not going. I won't be going into a formal proof because this is part of a discrete math course. But how will we prove this fact? So we are going to prove this statement using induction on the height of the tree. And the base case is when height is equal to 0. And we have seen this fact. When height is equal to 0, our equation is correct. Now the next claim is that let's assume that this equation is true for a particular height k, and let's prove this fact for a tree with height k plus 1. So if we have a tree so this is a tree with height k plus 1. Okay, so this is a tree height k plus 1, and these are subtrees of height k. So these are all, this is a complete binary tree, okay, and this is a complete binary tree of height k, this is a complete binary tree of height k, and this entire thing is a complete binary tree of height k plus 1. And I'm going to assume that this formula is true for a complete binary tree of height k. Now can I prove that this formula is true for a complete binary tree of height k plus 1? This is what I am going to prove. Now this, so since from our assumption I know this formula is true here, right? So the number of nodes here, so in this subtree I know this fact, n is equal to 2 raised to ni plus 1. So this is here, n is the number of nodes inside here, and again same thing here. So there also I know this fact. So n, so let me call this n left and so n0 for here, and so this is n internal 0 for here, and n1 for this, and 2n internal plus 1, right? So this is for here, this equation. Now, what are the total number of nodes in this tree? That is n0 plus n1 plus 1, right? So I have n0 plus n1 plus 1. This is the total number of nodes in this tree. N is equal to this, and I can write this. This is equal to 2 times ni0 plus and plus 1, right? Oh, sorry, this. Okay, yeah. So we have to add these 2 plus 1s, and this plus 1 comes there, right? Okay. Now so this I can take it inside, and I can write this is equal to. Okay. And what is this? This is the number of internal nodes in this entire tree. The number of internal nodes in this entire tree is number of internal nodes here plus number of internal nodes here plus this one, right? So this is equal to the number of internal nodes plus 1. So n is equal to exactly the formula which is written there. So what we have here is, we have proved that this is, so we have proved that the formula also holds for a tree of height k plus 1, and then inductively we can argue that, therefore, so we have shown that the this formula is true for the base case of height 0, and also assuming a particular height k, we have proved this to be true for k plus 1. Now, and therefore by induction we know that this is going to be true for any complete binary tree, right? This is our argument. Okay, so these are the particular properties of binary trees. We can ask some similar question. Another question is that I would want to see this equation in terms of height. So this here we have told that n is like this. Let me rewrite this in terms of height, and we'll stop this lecture with that. And let me write that. So this is with height. If I want to write, what is this saying? So this is saying height. So I'm going to take n plus 1 here. Okay, I took n, brought n plus 1 there. And I'm going to write less than or equal to 2 raised to h plus 1, right? So I'm going to take log here. So both sides log to the base 2, and here also, so h plus 1. Okay, and this h, so I can take the minus 1 there. So this becomes, right? So h is greater than or equal to log n plus 1 minus 1, right? Okay, and what else can I write? I can also write that h is, from here I can write, I can take 1 there. So I can also write h is less than or equal to n minus 1. Okay, so from now onwards I won't be using log 2. When I write, if I write log, it means log to the base 2. Okay, so this is a very important formula. You need to keep this in mind, and right, and see, sometimes in our in our lectures we are assuming that this tree, right? So this is a tree with just one node. We are taking its height to be 0, right? And this to be of height 1, etc. So, but sometimes people might view this to be of height 1 and this to be of height 2, etc. Okay, so sometimes people look at it that way, that this is of height 1, this is of height 2, etc. But we are going to see this as height 0, this as height 1, etc. And our formulas are like that. But if you had assumed this to be of height 1, formulas will slightly change. Okay, right. For example, this won't be h plus 1. In that case, it will be just h, 2 raised to h, and this will also be h. So this will be h is less than or equal to n. So this gives a better equation in that sense. If you see that as height 1, this will be h is less than or equal to n less than or equal to 2 raised to h minus 1. and similarly this will also change accordingly. It looks better, I agree, right? But we are going to use this. Good, and thank you.